welcome to Lecture 2.1, 5.3, Independence and the Multiplication Rule. So the first objective, identify independent events. So, two events, E and F, are independent if the occurrence of event E in a probability experiment does not affect the probability of event F. Two events are dependent if the occurrence of event E in a probability experiment affects the probability of event F. So they're independent if they are not affecting each other, and they're dependent if they are affecting each other. Let's take a look at this example. Determine whether the following events are independent of one another or not. So flipping a coin twice. If I flip a coin the first time, let's say I get heads, and then I flip it again, will the fact that I got a head the first time in any way affect what probability I'll get a heads or a tail the next time? No, it doesn't matter the fact that I got a head the first time. I just start again when I flip the coin a second time. There is no effect from one flipping to the next flipping. Okay, so these are independent. They do not affect each other. How about pulling two cards one at a time from a deck? Well, let's say I have a deck of cards, right? And I pull out one card. Well, the probability of picking this card, I have now removed that card from the deck, which means there are less cards in this deck. So when I pull a second card, it actually is affected by what I pulled the first time. The situation is now different. I have changed from what I'm pulling. So these guys are actually dependent. Now let's see, drawing names from a hat with replacement. So let's say I have a top hat, right? I pull out a name, I read it off, then I stuff that name back in, shuffle it around, and pull a new name. Well, actually, there is no effect. Because I put it back in, the probability of picking each of the items is exactly the same. So this one is actually going to be independent. When I pulled the first one and I replaced it, it doesn't change the probability of picking the second one. But now let's take a look at the next one. Drawing names from a hat without replacement. So this is saying I pull a name out of the hat, and then I pull another name. Well, once I pulled one name from the hat, that changes the probability of pulling all the rest of the names. So this one is actually dependent. I have changed the probability of the second try. Okay, let's take a look at disjoint events versus independent events. Alright, so disjoint events and independence are different concepts. They may seem similar, but they are different. Recall that two events are disjoint if they have no outcomes in common. That is, if knowing that one of the event occurs, we know the other did not occur. Independence means that one event occurring does not affect the probability of the other event occurring. Therefore, knowing two events are disjoint means that the events are not independent. Take a moment to ponder on that one. It is a little wordy. Let's take a look at example 2. Determine whether the following event is independent or disjoint. Let E be rolling an even number and let F be rolling an odd number. Well, we know that these guys are going to be disjoint because they have no outcomes in common. If you've rolled an even number, it's not possible to have rolled an odd number. They are disjoint. And let's see, the probability of rolling an even number from a die would be half. And the probability of rolling an odd number from a die would also be a half. Now, if we know that the probability of, however, if we're told that the roll of the die is going to be an even number, then what's the probability of seeing the event F? Well, because we know that the die is going to be even, the probability of seeing an odd number, oops, that was supposed to be my pen, probability of seeing an odd number now becomes 0 once we know that this is going to happen. So the knowledge that event E happens changes the likelihood of event F happening. Alright, let's take a look at objective 2, the multiplication rule for independent events. Example 3. Suppose you want to find the probability of obtaining, that should be gone, of flipping a coin twice and obtaining heads each time. What is the sample space for this experiment, and what is the probability of obtaining heads on each flip? Well, what's the sample space? Let's see. The first time we do this, let's say we get heads and heads. The next opportunity would be getting tails and tails. After that, we could get a tails, then a heads, and finally, we could get heads first, then tails. And those are all the options. So that's my sample space. Now let's see. We want to see what is the probability of obtaining head on flip 1 and head on flip 2. Well, let's see. That's only one probability where that happens. It's 1 out of how many possible ones? 4. So the answer to that would be 1/4. Well, let's take a look at the multiplication rule. If E and F are independent events, they have to be independent, note, then the probability of observing E and F is going to be probability of E times the probability of F. Example 4. In a game of roulette, the wheel has slots numbered 0, 00, and 1 through 36. A metal ball rolls around the wheel until it falls into one of the numbered slots. What is the probability that the ball will land on a slot numbered 17 2 times in a row? Alright, let's see. What do we know? Well, we know that there are how many possible outcomes? Well, we know there's numbered 1 through 36, so that is 6 outcomes. Sorry, 36. Whew, that is 36 different outcomes. But then we also have the outcome of 0 and 00. So that's going to be 36 plus 1, 2. 38 total outcomes. And then the probability of landing on 17. So what's the probability? Or actually, let me just write this up. What is the probability of 17? Well, we only have one opportunity to hit 17. So it's going to be 1 out of 38. Now what we want is the probability it'll land on 17 2 times in a row. So that means we want the probability, let me write this out. Probability of 17 on first try and second try. That's going to equal the probability of 17 on first try times the probability of 17 on second try. Well, what's the probability of getting a 17? 1 out of 38. Multiply that again by 1 out of 38, and we'll end up with 1 out of 1,444, which is approximately 0.00069. So that's the probability of getting a 17 twice in a row. That is a pretty low probability. I would not stake some money on that. Actually, let me go ahead and just box these two. Let's take a look at the multiplication rule for n independent events. So let's say you have an unknown number of events you're looking at. Event 1, 2, 3, and up to n. how do we find the probability? Well, the probability of E1 and event 2 and all the way up to and event n is going to equal the probability of event 1 happening times the probability of event 2 happening, times so on until we get to the probability of event E happening. And notice these are independent events. You'd have to make sure of that. These cannot be dependent events. So all you do is you just take the probabilities of all of them happening and multiply them together. For example 5, the probability that a randomly selected 24-year-old male will survive the year is 0.9986. That's not bad. According to the National Vital Statistics Report, Volume 56, Number 9. What is the probability that 3 randomly selected 24-year-old males will survive the year? And we are allowed to assume that these are independent. So, because there's no indication that the survival of one male affects the survival of others. At least that's the approach we're going to go with here. Well, let's see. We want to know the probability that all 3 males survive. To find that out, we're going to take the probability first survives, times that by the probability second survives, and multiply that by the probability the third guy survives. Well, what's the probability one guy survives? That's 0.9986. How about the probability that second guy survives? These are independent events, so we can use the same probability, 0.9986, and also 0.9986 for the third guy. Plugging that into our calculator, we'll end up with 0.9958. So there we go. That's the probability the 3 randomly selected males will survive. Pretty good. So what is the probability that 20 randomly selected 24-year-old males will survive? Well, let's see. That would be a probability of all 20 surviving. So that would be, let's see, probability first survives times the probability second survives up until the probability the 20th survives. So that means we have 0.9986 times 0.9986 all the way up until 0.9986. We have this number written out 20 times. Well, that's just the same as writing it 0.9986 to the 20th power. It's written out 20 times. Okay, let's plug that in the calculator, and what do we get? 0.9724. So if we randomly selected 20 24-year-old males, we'd expect all to survive. Well, we'd expect the survival to be 0.9724. Let's see objective 3, compute at least probabilities. So what does the phrase at least mean? Well, if I was to say I have at least 12 pairs of shoes, what I'm saying is I most likely have more than that, but I don't have less. I wouldn't have 9 shoes. I might have 13, 14, 17. But to say I have at least 12 pairs of shoes means that I have more than 12. Or for example, to say a person needs to be at least 17 years old to see an R-rated movie means that if you're less than 17, you wouldn't be able to watch the movie. But if you're older than 17, you can. So at least means greater than or equal to. Let's take a look at example 6. Compute the probability that at least one male out of 1,000 aged 24-year-old will die, during the course of the year, if the probability that a randomly selected 24-year-old male survives is 0.9986. All right. Well, we're trying to find, what are we trying to find? want to find that at least one will die. Okay. Well, we're trying to look at the probability that one or more will die. So, probability of 1 or 2 or 3 or 1,000 will die. Instead of morbid here. Well, what would that be? We would have to end up adding all these probabilities. The probability that 1 dies, plus the probability that 2 dies, and so on, plus the probability that 1,000 die. Tons of probabilities. This would take a really long time. So we're going to say, you know what? Let's try find a different method. Let's look at looking at least. So we want the probability at least 1 dies. So another way of looking at this statement is saying we want the total probability and taking away the probability that none of them die. So this is the reverse way of looking at it. It'll take way less time than trying to calculate the normal method up there by adding the probabilities up. So this will be 1 minus the probability. Well, what does it mean for none of them to die? Well, that means for all of them to survive. So minus the probability first survives, and second survives, all the way up to 100th survives, which we can write out to 1 minus the probability of the first surviving times the probability the second survives, and on until we get last one, the probability that the 100th survives. So how many times are we seeing this probability? Well, let's see, 0.9986, that's the first guy. Then for the second guy, we have the 0.9986, multiplying all the way out till we get to the 1,000th guy, which means we're seeing these numbers appear how many times? 1,000. 1 minus 0.9986 to the 1,000th power, because we see that 1,000 times. Plugging that into a calculator, we get 1 minus 0.2464, which comes out to 0.7536, as probably at least 1 dies. So, as mentioned, there are 2 ways we could do this. We could go ahead and take out the probabilities of all of them dying and adding them up, or we could just say, you know what, let's take a look at this a little differently. What about the probability 1 minus the probability that none of them die? And that's how we'd get our answer. So let's take a look at example 7. About 14% of the population of a large country is allergic to pollen. What is the probability? If 2 people are randomly selected, what is the probability that both are allergic to pollen? Well, this would be probability both are allergic. That would equal probability that the first guy is allergic times the probability the second guy is allergic. And let's see. What was the probability that it's about 14%? So the probability of picking that guy would be 0.14 times the other one, which is 0.14. Multiplying that out, we get 0.0196. That's a probability that both people are allergic to pollen. Now, what is the probability that at least one is allergic to pollen? Well, let's use that method we used up here. 1 minus the probability of the opposite. So the probability at least one is allergic. We can find this by saying 1 minus the probability that none are allergic. So that would be 1 minus. And what's the probability that none of them are allergic? Well, we know 14% are allergic. So let's rewrite the probability none are allergic to be the probability of first is not allergic times the probability that the second guy is not allergic. Well, if the probability of the first guy is allergic is 14%, what would the probability that he's not allergic be? Well, that would just be 100 minus 14, which would be 0.86%. So let's do this. 1 minus the probability the first is not allergic is 0.86%, or we'll leave it as a decimal. Then multiply that to the probability the second is not allergic, which will be the same probability of 0.86. Multiplying 0.86 times 0.86, 0.86 times 0.86, and we get 0.7396. Doing the subtraction, we have our answer is 0.2604. That is the probability that at least one person is allergic to pollen. Alright, that is that for 5.3. Please email me if you have any questions.